of October. Yay? All right. Oh, yeah. Okay, my dears, here we go. So in conditional probability, there is a condition that affects the second event happening. Okay, so for example, if you have probability of A and probability of B, and the event A affects B, then the conditional probability of A given B, is how you write it, that little bar. So you write probability of A given B is equal to the intersection over the probability of B happening. Yeah. Yes. Or let's say the probability of you eating chocolate cake is 1 out of 3. So if you ate this cake, what was the probability that it was chocolate? That kind of thing. Right? Yeah. And we're going to draw T diagrams and all that stuff. Oh boy. Rewriting this equation, just multiplying probability of B to the other side, you can find the intersection quite simply just by doing that. That's called the multiplication law of probability. Yay? Okay. And focus. We're good? We're good. Thank you guys.
Did you say cookie?
You had a muffin.
What kind of cookie? You're giving chocolate chip.
Good Lord. All right, now that Alejandro has his cookie, here we go. All right, so a useful application of this is like picking playing cards, or let's say rolling a dice. If probability of A and B are pretty much the same thing, like coming from the same outcome, then you can also switch this equation around. So the probability of A given B, where was that from? Oh, did I do this one? Okay, so probability of A union B. Oh, right. Which is the same thing as the probability of B union A. Yay. So you can switch everything around, and that's also probability of A times the probability of B given A. So what's the probability that the cake was that Lee would eat the cake if we knew the cake was chocolate? That kind of thing. I think we talked about chocolate, and then if we knew you ate the cake. Yeah. Oh yeah. Oh yeah. Oh. Oh my goodness. Oh my goodness. Okay. Here we go. 100% that he has eaten a chocolate muffin. Oh man. Suppose a jar contains 7 red discs and 4 white discs. 2 discs are selected without replacement, aka you don't put the disc back. Yay? All right. Find the probability that both discs are red. So we're looking for just shorthand notation, the probability that the first disc was red, so I'm going to go red 1, and, so intersection, the probability the second disc was red. Yay? Okay, so for the first probability, we know the probability of first disc being red, there's 7 discs out of 11, right? And the probability that the second disc is red, since we didn't put it back, is 6 out of 10. Yeah. So, get this, the probability that the first disc is red and the second disc is red, using that law before, we can switch it around. You can just take the probability that the first disc was red times the probability that the second disc was red, given the first disc was red. Right? Oh, I didn't write this correctly. This is the probability that the second disc was red, given the first disc was red, is 6 out of 10. Yeah, that's where I messed up. So just multiplying it together, that's 7 out of 11 times 6 out of 10, so 42 out of 110, which reduces down to 21 over 55. Yay. Yay? Okay. Probability that both discs are the same color. So either red, red, or white, white. Okay? So, there's a shorter way to write this, but just to lay it all out. You're looking for the probability that you have red 1 and red 2, or you have white 1 and white 2. Like so. Right? And remember that, let's put it off to the side, union means to add, and intersection means to, do I have it backwards? Yeah, nope. No, and union means or, add, intersection is multiply, yeah. Okay, so this would be PR1 times PR2 given R1, right? And then union would be add, and then PW1 times PW2 given W1, like so. Yeah? Okay. So probability that the first one's red? Yeah, just putting back those numbers. It's 7 over 11 times 6 over 10 plus, if they're both white, in the first time it would have been 4 out of 11 times 3 out of 10. Oops. Yeah. Okay. 42 out of 110 plus 12 out of 110 gives us 54, which reduces down to 27.55. Yeah. Yay? Yay. Yeah. Oh, speaking of structure, let's draw a tree diagram. So IB loves tree diagrams, and they're pretty easy to construct, because if you know one leg of the tree diagram, you just subtract it from one, and you got the other leg of the tree diagram. Okay? So this is like, yeah, this is another way to do your results. So here we go. All right. So if necessary, you can draw a tree diagram, so that way you can pick out all the parts of the equation. And especially when it gets to Bayes' theorem, which we'll get to at the end, there's a lot of parts of this equation. Okay. Here we go. The weather records indicate that the probability that a particular day is dry is 3 out of 11. Liverton Villa is a soccer team whose record of success is better on dry days than on wet days. Probability that Liverton will win on a dry day is 3 out of 8, whereas probability that they'll win on a wet day is 3 out of 10. Liverton are due to play next match on Saturday. Draw a tree diagram of the possibilities. Liverton? Ooh. Oh boy. Okay. So, usually it splits up. So depending on the weather, it's either dry or it's wet. Yay? So we start with the weather. Yay? The probability that the day is dry is 3 out of 11. Yay? Therefore, the probability that it's not dry will be just 1 minus that, which is, that's a not dry, by the way. There's a exclamation or apostrophe there.
Oh, then it's just.
Yes, sir. 8 out of 11. Like so. Okay. So that's the weather. Then, depending on the weather, they either win or they don't win. So we're given that the probability that they'll win on a dry day is 3 out of 8. So the probability that they'll win, given that it's dry, is going to be 3 out of 8. Okay? Therefore, the probability that they won't win, given that it's dry, is going to be 5 out of 8. Now, and then for the second one, again, they'll either win or they won't win. So the probability that they'll win, given that it's not dry, which is on a wet day, so not dry, is 3 out of 10. And the probability that they won't win, given that it's not dry, is 7 out of 10. So check this out. If you just follow the line, you just multiply the probabilities out. For example, for probability of dry and then they win, it's 3 times 11 times 3 over 11 times 3 over 8, and that will give you the result for when multiply is and dry. Yeah, right? And this would be not win and dry. Of course they're going to win. This one would be win and not dry. When given, oh sorry, and. And then the multiplication of this line would be given not win and not dry. Okay, so probably they're going to win. Okay, so the probability that they'll win is going to be the probability that they'll win and dry plus the probability that they'll win and not dry. True? Okay. So again, just multiplying the veins along this way. Win and not dry is going to be 3 out of 11 times 3 out of 8. Okay? And then win and not dry would be 8 out of 11 and then 3 out of 10. So okay?
I have 9 over 88 plus 24 over 110.
Plus 24 over 110, which is?
Oh, I don't know.
Oh, I don't know.
I said 24 over 110 simplifies to 12.
Oh, yeah. Anybody got the calculator out? Yeah? Just stick it in there. Good old Aria. So dependable. Look at you. 9 over 88 plus 24 over 110 is 141. 440. Yay. Yeah. Cool. Okay. So, once upon a time, 3 Saturdays ago, Liverton actually won their match. What was the probability that it was dry that day? Okay. So, we're looking for the probability that it was dry given that they won. Right? Which is probability that it was dry and they won over the probability that it was that they won, which was like the first formula we talked about. Since A and B are happening on the same time, we can also just switch that around. So probability of win and dry over probability of winning, which is what we just calculated, right? And we know win and dry is win and dry 9 over 88. So it's 9 over 88 over 141 over 440. Yeah, Aria, you got this? Cool. 55 over 94. Sounds about right. Sweet. Oh boy. All right. That's not correct? I believed you. Just kidding. What do we got? Is it 16 over 47? 15 over 47? kid ate fish cake on a stick. Like, you don't even eat anything else that she used to do at Red Jelly. And she ate fish cake on a stick. Anyway, I love fruit. So, if you ever bring Korean food, I'll be happy to taste. All right, here we go. The card thing that we did in the back, just because we replaced it, right? So A and B, the two events, like the first card versus the second card, would have been independent. So the multiplication law for independent events is you can just multiply out all your events. If you want certain things to happen in order, you just multiply out your events. So, for example, an example of an independent event is rolling just one die, right? You roll one die 4 times. What is the probability that 3 out of the 4 rolls is going to be a 6? Yay, so it's just one die, so it's either 1, 3, or 6. So, we're going to write out all the possibilities, right? Here we go. Either your first roll is a 6, your second roll is a 6, third roll is a 6, and then you can have anything for your fourth roll, right? Yeah. Or your first roll is a 6, your second roll is a 6, your third roll is anything, and your fourth roll is a 6. Or first roll 6, second roll anything, third roll 6, and fourth roll 6. Or first roll anything not 6. Sorry, anything but 6. And then second roll 6, third roll 6, and fourth roll is 6. Okay? Okay. So yeah, let's do this. Here we go. So to find all those probabilities, find each one, and then you're just adding them all up together. Yeah. So for the first probability, it's 1, 6 times 1, 6 times 1, 6 times 5, 6 plus 1, 6 times 1, 6 times 5, 6 times 1, 6 plus 1, 6 times 5, 6 times 1, 6 times 1, 6 plus 5, 6 times 1, 6 times 1, 6 times 1, 6. Okay? Well, I mean, we can simplify this equation. It's the same thing 4 times. Yeah, it's just 4 times. We have 1/6 to the third every time times 5 over 6, which is what Alejandro is saying. 4 times what? 5 over something.
No, I found it like it is 5 over 1,000.
Oh, I got 5 over 324. Did you multiply by 4?
But then I did all of them individually.
Oh.
Then I added them all together.
So reduce.
Because like my final answer is 20 over 1,200.
You can't? You can reduce it. Yeah. You should be able to reduce it by 4, actually. Right? Actually, let's just go straight to the answer. Yeah, 5 over 324 is that answer. Sweet. Okay, Miss Bays, this one's for you. Here we go. You get it? Okay. All right. So, if you want to go over how to simplify like partial fractions and stuff, Bayes, not Mrs. Bayes, but some Bayes found a way to use partial fractions. Meadow talked about partial fractions, kind of, sort of. Do you remember partial fractions? Something.
No, we used it in
Finding the derivative, yeah, because you had to split it up so that way you can find. Even you can do it in integration too, because you can find the integral of each individual thing. Yeah. Nah, it's like you take the denominators and then a plus b plus c and then find. Yeah. Anyway, if you do some fancy fraction work with the first thing that we talked about, you could you could derive this theorem. It's Bayes. So you can see it's the same thing. This would be like a P of A union B over P of A. Well, P of A could also be written as that. Right. Yeah. Good news. Good news. Bayes is in your formula sheet. There's no need to memorize this. It's on your formula sheet. It's a good one to have. All right. Yeah, it's a good time. All right. So if you don't know, I'm from Vegas, and in Vegas they have slot machines. So here's the deal. Right? Yeah. Some slot machines pay out more than others, and depending on the location, like they like to have the higher paying out machines, like by the front door, so people think that you're winning in that casino when people are walking by. But so there you have more chances of winning from the front door than you have like in the middle of the casino. Nobody cares over there. But they will give you free drinks as long as you're sitting at the machine. Just saying this. Here we go. In a casino, there's three gaming machines of two types. X and X bar or X naught, which look identical. They're the same Wheel of Fortune machine. Yay.
So
but the problem,
sit at the machines, it'll slip.
Happens, yes. One time because I don't gamble.
Yeah,
right? Yeah. You look like you're gambling. That's it. But only when you're of age. Okay, so 21, you go and you sit and pretend to gamble, but don't because it's not healthy. All right, here we go. It's a good time. Probability of choosing the first machine is 1/3. Probability of picking the not machine would be 2/3. So I mean, I'm thinking the winning machine is 1/3 and the loser machine is 2/3 because there should be more loser machines because the house always wins, right? I don't know. That's what I'm thinking. So probability of winning on the first machine is 1/3, while probability of winning the other machine is 1/4. Wow. Yeah. You can choose a game machine at random. What's the probability to choose machine X? So this is a good deployment of one Bayes theorem. Second, the tree diagram. Let's do it. Here we go. Yeah. So choosing a tree diagram, you either pick machine X or you can pick machine not X. Okay. Probability of picking machine X is 1/3. Machine not X is 2/3. Okay. And then two possibilities, win or not win. So probability of winning given you're in machine X, is equal to 1/3. Which means the probability of not winning if you're on machine X is 2/3. There you go. 2/3? Whichever. All right. Probability of winning if you're on machine not X says it's 1/4. Yeah. So the probability of winning given not winning, not X is 3/4. Is true? Okay. So good old Bayes theorem. Let me keep that up there. B-A-Y. Nope, it's not. It's B-A-Y-E. Bayes. So, like, his name was Mr. Baye. Yeah. Right. All right. So, we're looking for the probability that you chose machine X given that you won. Yay? So, the probability that you picked X given that you won. So pretend, just switching the letters around, X would be B, and then A would be the winning. So it would be the probability of winning. Nope, probability of X. Sorry. Yeah, delete. Okay. Probability of X, right? Times the probability of U1 given X, true? Over this same thing copies down. It's the first part of the bottom equation. So probability of X, probability of winning given X, plus then the probability of not X times the probability of winning given not X. Not X. Yeah. All right, let me clean that up. Not X. There you go. True? And because of the tree diagram, we have all those things. They're all there, right? Probability of X. Yeah. Probability of winning given you're on X. 1/3. And then this thing just carries down, so 1/3 times 1/3 plus probability of not X is 2/3. Yeah. Times 1/4 is your chances of winning. So that's 1/9. 1/9 plus 2, 1/6. Yay? Which simplifies 2. Okay. Put the 18 to the top, 2/5. Sir. That's it. So there's a 2/5 chance that you were on machine X. Good to go. Okay. Again, next week, working on doors half the time, working on M&M lab half the time. Yay? All right. Thine assignment then, over the next 4 days, 1 through 11 odds. And they all lived happily ever after. Yes, sir. Absolutely. Next time. So